I'll talk about work today that was done by Christiana, a PhD student who's about to finish her degree soon, and she's in the audience. It was done in collaboration with Andrei Erpenbeck, a postdoc who's shared with Emmanuel Goul, my partner in crime for all things Inchworm, pretty much, and Evgeny Barlev, who's my longtime collaborator and the guy I sat next to while I was a postdoc at Columbia. Well, let's start by telling you guys a little bit about my group in general. I mean, we are a very much methodology-focused group. Most of our work is pointed in that direction. This is an aging picture now of the group. We're located in Tel Aviv. We do quite a few things. I would say what we're probably most well known for is our work on Inchworm Monte Carlo. It started at Columbia, and we've developed a series of algorithms that are good for solving quantum impurity models. The first things were for dynamics of non-equilibrium impurity models at short and intermediate times. And this is what will lead to what I'll talk about today. We had another algorithm for using the same ideas that were used to solve the dynamical sign problem and these things to solve multi-orbital sign problems and imaginary time dynamical mean field theory calculations. And we have a more recent work on doing this kind of thing directly in steady state, but in real time. And well, this will be less methods focused than most of my talks. I'm going to talk about localization. So first, let's do a little bit of an intro. So when we think about thermalization, it's easiest to think about a classical system. So you have a gas in a box, and if I put the gas in some strange arbitrary state, like say I put all the particles halfway through the box, then I would expect that after some time I would see a state that would be typically sampled from a thermal equilibrium of some sort. And the mechanism for this classically is chaos, right? So the system will eventually thermalize, and we get a state drawn from some sort of thermal distribution. But we know that quantum mechanics is linear. So actually, if I start my system in some state, I will actually have the same probability of seeing every eigenstate forever. If I start in an eigenstate, I'm in that same eigenstate for the rest of time. So we don't really have that concept of thermalization in quantum mechanics. Now, you can think of systems that do seem to thermalize, and this question is really only interesting for closed systems. If your system is open, you have some sort of bath, then it will effectively thermalize with that bath. But if your system is closed, then you can think of thermalization in terms of all kinds of physical observables which seem to thermalize. So if you look at a system which starts, say, in some non-thermal state, I put all my particles on odd sites, and I allow that system to evolve in time, I would eventually expect to reach a thermal state where all the sites are equally occupied if the system is thermalizing. But it turns out that some systems are not thermalizing, and they will forever be trapped in some state that captures some information about the initial state, or that is not characterized by, let's say, what you would expect at equilibrium. And there are definitions for what you should expect and some understanding of when you should expect this kind of thermalization behavior. So one of the interesting cases where you don't necessarily thermalize is localization. So we know from Anderson's famous paper that non-interacting systems, if you put some disorder in your Hamiltonian, can, in many cases, have eigenstates that are just localized in space. And then if you put something somewhere in space, it may never go far away from that original position. And actually, this is a non-interacting effect. It's very difficult to observe cleanly. This was done in optical systems for phonons, where you have essentially no interactions. And you can construct a system which is like, let's say, a non-interacting boson model. Start your photons in some part of the system and watch how they evolve across the system. So this axis would be a simulation of time for a 2D system. And if your system is not localized, things will expand, maybe ballistically, maybe diffusively. And if it's localized, then everything will stay in some small area of the system, will never expand, and you don't really thermalize. And from Anderson's original paper, it was at least somewhat clear that this thermalization could happen in cases where you do have many body interactions. But Anderson was thinking of the non-interacting case because it was solvable. So, and I should probably mention that, this, even though this field technically exists since the 50s, there was this work that came out of Columbia in the aughts, which really started the modern incarnation of it, and it's raised a lot of excitement ever since. So this is the field that we now call many-body localization. It's about localization in systems which do have interactions. Now, we know that 1D and 2D systems will always localize if you have any sort of disorder, at least in the non-interacting case, right? So this is just simple Anderson localization. In 3D, you have some kind of mobility edge. So there's an energy threshold for a given disorder that sets which of your states are localized and which are delocalized. Then you can look at all sorts of high-dimensional cases. And it's not, at least to the best of my understanding, this is not a fully closed question. But we think that when you go to high dimensions, localization becomes at least weaker. Okay, and there are many reasons why that would make sense. But for instance, there's this relatively recent study that claims that if you look at a beta lattice, which is quite similar to what I'm going to do today, then at the limit of high dimensions, the strength of disorder at which you will start to see localization rises with dimension, diverges at high dimension. So you would need very strong disorder to see any sort of localization effects when dimension is big. And that means maybe it's not as interesting to investigate. Now, there are other kinds of localization, and one kind is stark localization, which is a very simple, again, non-interacting effect. So if you think of a double well and the first two states in your double well, then we know that we'll have a symmetric one and an anti-symmetric one, right? Just from the symmetry of this little Hamiltonian. And then if I break the symmetry and I raise one well and lower the other, I expect one of my states to localize around the low well. The low energy state will localize around the low well, and the high energy state will localize around the higher well. And I can extend that to a sequence of wells, which is a little bit like a lattice in an electric field. And what you would expect to find, and you can prove that this indeed happens, is that you would have one state localized approximately around each well, and some sort of localization length emerges. So a constant electric field also results in localization in the non-interacting problem. So what happens if you have many body effects? Well, people have explored this both numerically and experimentally. So there are indications that stark localization can survive interactions, just like Anderson localization. And finite interaction strength may not always break it. Most of the numerical studies are done in 1D, in something like matrix product states dynamics. There are a few other things that are done. And there are experiments, for instance, in ultra-cold atoms. So this is a system of atoms on a lattice, and you start them in some state where you have up and down atoms arranged on odd and even sides of the lattice, and then you let them evolve in time. And if you have some interactions and no electric field, they will relax. So eventually everything will be essentially at half occupation of either spin. If you add an electric field, then they seem to localize, and you see something where the initial state is somehow imprinted for as long as we can measure on the dynamics of the system. So one thing that you can wonder about is what happens if the system is very big, whether at the thermodynamic limit you still have this localization. And people have been exploring that. Of course, both experimentally and numerically, that can be hard to check. But people have done, for instance, MPS studies at large system sizes and looked at the dynamics of how something expands through the system. Again, my collaborator here, Evgeny, has done a couple of these studies. And what you see is that for a small system, the system localizes and then delocalizes after some time scale. So whatever disturbance you've put into the system, it will spread out, it will stop spreading, and then after some time it'll spread again. And the time between these two spreading events increases approximately exponentially with system size. And there are some analytical arguments for this, but there's no proof that this really happens. It's interesting that if you look within matrix product states, there's a sharper way to see this, which is looking at the bond dimension, or something which corresponds to the amount of entanglement entropy in the system, and also how hard it is to simulate. So if you look at a small system, then after some time, the entanglement entropy explodes. But if you look at a larger and larger system, then you have a longer time before that happens. And eventually, actually, longer systems are easier to simulate than shorter systems, because this localization is stronger in a larger system. Okay, so what we set out to do is look at models that are tractable in the thermodynamic limit, and we went at this from the DMFT perspective. So of course, in this forum, I don't have to introduce that, but in the infinite dimensional limit, we have a mapping onto an impurity model. And then if we can solve the dynamics of that effective impurity model with the addition of some self-consistency condition, then we can learn what happens to some extensive high-dimensional model exactly in principle. And we're not the first to think about it in this context. So there's a nice paper by it has escaped the references somehow, fallen off the bottom of the page, but it's by Martin Eckstein and Philip Werner. And they have this nice PRL showing that if you do this for a hypercubic lattice with an electric field along one of its diagonals at the high dimensional limit, and you apply an interaction and an electric field, then you get a response that depends on, of course, both of these parameters and the current. And what happens is that if you are in what they call the DC regime, then you will have a long time response where the current always goes to zero, essentially because the system is thermalizing to an infinite temperature in this case. And that response looks like it's like the current is linear with the field to within something that has to do with the effective temperature. There's another regime which happens at stronger field where you see this oscillatory behavior in the current, and you still eventually relax to a state that has just no current, but the response is more like an AC response. Nevertheless, this system always thermalizes, and one could ask whether that is real physics or whether just localization, right? Real localization never really happens here. And it's not entirely sure that you can answer this within the weak coupling approach, I would say. Okay, so we did something quite similar to this. We constructed an even simpler model than that. And the idea was basically just to make this easier on ourselves, right? We could have gone with a hypercubic lattice. It's not necessary to do this, but there is some sort of manifold of models that's interesting to build and very simple to treat from a theoretical perspective. So let's start with the model that we're not solving, but that we're sort of going to construct a model that is, let's say, related to this model. So think of, say, a 2D square lattice. In that 2D square lattice, we have some sort of initial condition, which in this case is a spin density wave. And that spin density wave is arranged in the direction of the field. Okay, so we're still applying the field across a lattice diagonal. If we look at the sites, we can see that there are 4 types of sites in this model. And we can construct a unit cell built out of these 4 unique types of sites. And essentially, that will give us, every cell in the model, every node in this lattice behaves like one of these 4 sites. And then what we do is we look at each of these and we see how many neighbors of each type it has. So a node of type 0, a site of type 0, has 2 nearest neighbors of type 3 and 2 of type 1. A node of type 1 has 2 nearest neighbors of type 2 and 2 of type 0, and so on. So now what we do is construct a model which is a beta lattice, because that has a really simple DMFT self-consistency condition, where we just set the number of, or the proportion of neighbors of each type according to the lattice that we were inspired by. In this way, we can have a beta lattice that is inspired by a 2D cubic lattice or a 3D cubic lattice or any other type of model. There's a set of different things that we can do which express dimensionality, even though the model will always be infinite dimensional. And that's kind of nice. And also, because it is technically a bunch of beta lattices, then we would just be solving 4 impurity problems with a self-consistency condition that requires no numerics and no lattice solver. It's just essentially inserting the Green's function from the previous iteration into the next iteration. So this is quite easy to do. And then essentially, if we use a parallel substitution, dividing this thing into layers, each of which has a constant potential, then we can solve this kind of model in a constant electric field quite easily within the DMFT, assuming we have the right type of non-equilibrium impurity solver. And the numerical experiment that we're going to do is to look at how density waves or spin density waves of this type relax as we allow them to evolve in time, given that we have some Hubbard interaction and some constant electric field in the system. Okay, so let's see what this actually looks like. And the first thing we do is we take a system like this with a density wave with a periodicity of 6. So we have 6 types of unique sites. And we plot the probability of a site at any given time being having a populated spin-up, right? Or the spin-up occupation of each site. So for even sites, that starts at 1, for odd sites, that starts at 0. And if you have no electric field, then at long times, all these probabilities will just relax to 0, and your system thermalizes quite nicely. If we turn on a small electric field, it still thermalizes. For a large field, then something else seems to happen, right? At least within the accessible timescales, this seems to not thermalize. Now, first thing to notice is that you have these dashed and solid lines here. So these are two impurity solvers. Both of them are approximate. So it's the non-crossing approximation and the one-crossing approximation. So two of these so-called large N approximations. You can see that they're different from each other, right? So this is not a converged or numerically exact result. However, notice a couple of things. The OCA gives you stronger dissipation when you do have localization, which makes sense, right? It has more relaxation mechanisms built into it. However, the OCA also gives you somewhat stronger localization when you have localization. So that tells you that maybe this is not complete garbage. We'll have another way to check this in a moment.
Guy, sorry to interrupt, but aren't you missing a power of the, isn't there a typo in the first equation missing a power of the gradient?
Where?
Grad mu, it's d mu grad mu?
It's d mu grad mu, yeah. Oh, okay, yeah. So this is not Einstein summation, right? This is okay. Right? This is like a fractional diffusion equation. Okay, so d is a function of mu. That's the idea here. This is not a relativistic equation. So okay, so you know we think this is somewhat reliable. We can do a little bit better than that because we have these Inchworm type methods. So we can look at these populations at a set of times with NCA and OCA, and also with the exact solution that we can get, at least for short times and for small, let's say, numbers of impurities with Inchworm. And we can essentially see that the OCA is quite reliable in the regime that we've picked, which is why we've picked it. We can also see that there's a point where the Monte Carlo fails and that we forgot to remove. That is fine. So now the next thing that is interesting to do is to think of this as sort of diffusive behavior. Okay, if we want to think of this as transport, then we have some initial condition, and that initial condition is changing as a function of time until you're relaxing to some equilibrium state. So quite generally, you could think of this as some sort of diffusion process, or at least generalized diffusion process, where you have some sort of exponent that might be different from the normal diffusion exponent. So if you Fourier transform with this equation, you look at the Fourier components in space of these sites, then you get something relatively simple, which at small wave number should, you know, give you some kind of hydrodynamic-like physics, right? And then you can extract, if you look at these K components, you can extract from them a diffusion coefficient and a diffusion exponent if you have data at different wave numbers. So essentially, if we have a few different spin density waves with different wave numbers, we can extract from them diffusion coefficients and diffusion exponents as a sort of analysis of if this is the diffusion process, and if it is, then what kind of diffusion process it is. And you can see, right, if we plot this in Fourier space, that it kind of makes sense to do this, at least for small fields or no fields. It may not make great sense to do this for large fields where really the dynamics become localized. Nevertheless, we can try and do it. And then we use this equation to plot all the curves together and hope that we see some kind of collapse. So without an electric field, when you plot this kind of quantity, all the diffusion curves for all the different systems fall on the same curve, and you can extract diffusion properties. Interestingly enough, they still do that at very large fields where it seems to be localized. But I would argue that even though you can get a mu and a d from this, you probably shouldn't. So let's not do that. So when this looks nonsensical, or when it begins to look nonsensical, we will sort of start to gray our results out, and then we'll just stop plotting. And then you can look as a function of the electric field at different system sizes, so essentially approaching the hydrodynamic limit. You can look at your transport exponent and transport coefficient and see whether they are scaling in the hydrodynamic limit to something that makes sense. And this is something that we have a hard time converging exactly, but we do see at least some trends. Okay, so one should take this with a grain of salt. We are not at the small k limit, but we can come quite close to it and get something that we can learn something from. So once we gather all our data together, then essentially we can look as a function of the electric field at, let's start with the diffusion exponent at different interaction strengths. And what you see is that at small interaction strength, you go from an exponent of 1, which is normal diffusion, to something which is subdiffusive. And this is quite common when you have some sort of localization or localization-like process. And then as you increase your field, it actually comes closer to the diffusive limit again. Okay, so diffusion becomes faster. Now the diffusion coefficient is always decreasing, or mostly decreasing throughout this range. It maybe increases a little bit in the beginning, but when you want to characterize, rate of diffusion, this is probably the more interesting quantity to look at. So again, we go from diffusive to subdiffusive and maybe back to diffusive, and then we are essentially localized. As we go to larger interaction strengths, you see that you actually go all the way back to diffusive behavior, and then you go back to subdiffusive. But if the interaction is around 3, then you actually become super diffusive at some point. So it seems that at this point, the field, together with the interaction strength, gives you a diffusion process that is more efficient at delocalizing your spin density wave than what you would get with just normal diffusion. And what you can sort of work out is that this happens when your field is resonant with the local excitations or the atomic limit excitations in your system. So essentially, when you can excite an electron locally with your electric field, you get much quicker diffusion processes. Then when you increase your field again, you become localized again. So you see this very non-monotonic behavior in the transport exponents, which to the best of my knowledge has not been seen before. Whether this is completely reliable, we don't really know. So one source of error comes from the fact that most of this is done with OCA. Again, we have arguments why that's probably reliable in at least the edges of the regime. That seems to be okay, but one should do this with a better method to be sure. And the other thing is the finite size scaling, which again, we can draw some conclusions about, but it's not bulletproof, let's say. So I'm pretty much out of time. So I guess I should say it's possible to formulate a bunch of DMFT tractable models of clean many-body systems that have localization physics. And these are at the thermodynamic limit, which is quite unusual for many-body localization, where almost everything is done with small systems with finite size scaling. The only finite size scaling that we have is with the density wave, right? So it's hard to go still to the hydrodynamic limit, but we are at the thermodynamic limit. then if you have good impurity solvers, you can solve these things and learn something about the system. When we did this, we found at least some evidence of localization that occurs at the thermodynamic limits. One thing that we found here that we thought was surprising is that sometimes actually you have faster than diffusive transport when you combine interaction with an electric field in the right way. And yeah, I didn't mention, but you can actually connect that to the existence of a current. When you have this super diffusive transport, you also have an enhancement of the current in the system. And I think that's pretty much what I have time for. So thanks everyone for listening.
Thank you very much, Guy, for this very nice talk. We opening the talk for questions, Antoine.
Yes, thank you, Guy, for the stimulating talk. I have a question about what we should call localized or not. So,
sure.
Am I correct that mu smaller than 1, I think in your notation, means obviously subdiffusive, so slower than normal Brownian diffusion? But
yeah, mu larger than 1 is subdiffusive, mu smaller than 1 is superdiffusive.
Yeah, okay, so the opposite thing.
Yeah.
But still not really localized. I mean, when mu is larger than 1, I would expect that you know, the current or particles can still spread, or the wave packet can still spread, but it will spread slower than diffusive.
Absolutely, yeah. So everywhere where you have subdiffusion, this is not localized. The localized is where this fades away, and really you can no longer fit a diffusion experiment, a diffusion equation, right? So if you look at the data, right, this would be localized. Now, I might be able to, you know, give you a very small diffusion constant here, probably with a very large error bar, but I don't think I should. Right now, can we prove that this is really diffusive, that this is really localized for infinite time? Definitely not, but you know, we can follow it for some time, and you see that it looks quite strongly localized. That's, I think, the best I can say from a numerics perspective.
Okay, thank you very much.
Further questions? Adriano?
Yeah. Can I ask a question about the current in the last slide? What kind of current is that? I mean, is the total current, or is measured with respect to the electric field? I'm asking because there was a result many years ago from Camille Yaron and Gabi about the transverse localization. When you take a system like this, when you apply an electric field, you know that there is a localization like yours, but there is a in the transverse direction to the field. So you still have the carrier still can carry the current in a steady state. Now the difference is that in that case you have a thermostat that we introduced a long time ago to actually have a finite current at the end. Here you want to localize, so you don't want to have a thermostat, otherwise localization will never actually take place, maybe just for very large electric fields. So what is the current here?
So again, because this is Stark localization, you only have localization in one direction here, only in the field direction. So everywhere else, things can, you know, things can travel freely. So this is the current in the field direction between neighboring sites. So the best way to think about it is in this picture, right? So this would be the current in these directions, right? Between site 0 and its neighboring sites 1, or its neighboring sites like that. Okay, it's always like that, and you know, it is actually measured on this effective Bethe lattice, which is a weird description of this model. Okay, now in this case, because this site is actually decoupled from all its neighbors within the same layer, then you also will not have diffusion in the other direction. But generically, right, if I had you know, a Bethe lattice inspired by a 3D version of this model, then I would have that as well.
Okay, I think I saw a hand raised by Dita. Yes. You're muted still.
Yes, yes. Okay, thank you very much for your talk. I thought this was very interesting. I have two questions. One related to this fractional diffusion equation. I mean, usually one has a Laplacian, the Laplacian proper. To what extent are your results influenced by this fractional diffusion equation?
Well, I mean, the question is, right, I mean, even defining this fractional Laplacian is a little bit iffy, right? And people usually think about it in terms of random walks. So there is some, you know, Yossi Klafter from my department is has the famous review about this. But essentially, the question is whether you get a mu here that is different from 1. Right? If I can fit a mu of 1, then I don't need to think about this at all. And in fact, what we find here is that, you know, it does pay to change the mu from 1, right? This data is not fit well if you keep to normal diffusion all the time. And this is kind of common practice in the MBL community, right? I have another paper, right, with Evgeny about subdiffusion in 1D spin lattices, and people are you know, very much used to thinking about it like this. But yeah, I think this notation I found it alarming as well.
Okay, now I understand your point. Thank you.
Yeah.
Can I ask you another question?
Of course.
Sure. You concentrated on spin transport, or you concentrated on the spin starting from a spin density wave. How much more difficult would it be to start from a density wave?
It's absolutely the same, right? So one thing that we considered doing instead was just to start with all sites being either you know, double-ons or whole-ons, and that is no more or less difficult. We started from this just because it was a little bit more similar to things that other people did experimental. Like you were thinking about this experiment, for instance, where they started with a maximal spin density wave. But it's in terms of the methodology, right? This is just a different initial condition for the impurity problems.
By the way, may I pronounce your first name Guy or Guy?
It's Guy. Yeah, it's the Israeli guy, not the French guy.
Okay, thank you.
Thank you very much. Are there any further questions in the audience? Maybe I can ask one. So you mentioned different impurities over Sky, right?
Yeah.
What is your general perspective on, let's say, non-equilibrium impurities overs and your specific one on problems with Stark localization?
Well, first of all, of course, I like mine the best. But well, so this kind of problem could be done with any non-equilibrium impurity solvers, and you know, there may be other things that are maybe a better choice in this case, things that can easily go to a long time and maybe even are approximate. So you know, if someone can write a good two-crossing approximation that scales well and do the dynamics here, then that would be probably essentially exact. One thing is, you know, we do this for a lot of regimes and a lot of different system types. Because we have these interim things, then we can look at first, second, third order, and so on, and see when we really need to go to 8th order or when we don't. And this is not a strong correlation study, right? Like everything here, we can do at relatively high energies. A lot of the MBL community is interested in infinite temperature, really. So you don't necessarily need the best impurity solvers. However, because it's a funny regime and you may not be very familiar with it, it's at least good to have something numerically exact to do some checking.